So hello everyone, welcome to the week 11 of the tutorial sessions of this Sobolev space and partial differential equation course. My name is Shammi and currently I'm a PhD scholar at the Department of Mathematics, IIT Delhi. So in this week we will discuss problems based on this Hille-Yosida theorem and this C₀ Semigroup theory. So in this week in the videos you saw about this C₀ semigroup and about the Hille-Yosida theorem. So these are like quite helpful in this evolutionary equations to solve these type of evolutionary equations. As we will see, we will borrow one result, and we will see that with the help of that result, we are able to uh, prove about this generators. And with the help of that, we will solve some PDs. And before that, we will see some examples that how we have this some example of the C₀ group and like in the very familiar Lebesgue spaces, so that we are like very we have a better understanding of this C₀ family groups, and once that is there we will see some applications of solving of PDs. So let us start. The first question will be based on the translations. Translations on LP spaces. Of course, we will the domain is not defined, but we will change we will domain take to be a subset of a real line with different examples like that. Basically, exhaust all the cases, more almost all the cases, and these translations will actually form a C₀ semigroup. So as you will see. So if we're taking for P1 to infinity, we define, let's not say define, let's um, show that for this, show that the following are following are C₀ semigroups on respective spaces. So the part A is on LP are define TT belongs to the L of LPR by TT fix is nothing but just translation by T f of x minus T for all x in R and for all f in LP spaces. And my T is actually in and my T actually is in So I have to show, we have to show this is a C₀ group, C₀ semigroup. So one thing is clear that this being a translation, it's this LP norm is not changed because by the change of variables. So clearly by change of variables, we have we have TT is an isometric isomorphism for all P in R. So it's an isometric. Again, it's we are. I'm taking T as a parameter. This again forms the group. Being we have all the properties. So like not in the semigroup, we have the group property here because of my translations in R. And it's identity when I take T equal to 0. And inverse is like this. If I'm taking D, the inverse will be minus D. TT and then T of minus T. So it's like in fact it makes a group as well. So moreover, T is a one parameter group. And consider now F to be the characteristic function of AB. The characteristic function of the interval where I'm taking A to be again less than B and A and B both are in real line. Then we have T of T acted on F. It actually This is nothing but this thing converges to F only as T tends to 0. So this being a characteristic function of an interval, we can generalize to once we have this thing. So ultimately, we have to want to prove the final property that it's like identity only as T tends to 0 point wise. So if I take this characteristic function, we have this thing. Once we have this, we can extend this to indicator functions as well. And since I'm able to extend this for indicator functions as well, like with we can use the dominant convergence theorem, or being they are we can use the DCT to eventually get this. And once that is there, we know that the indicator functions with with support being finite, these are dense in the LP spaces. Now, a span of these indicator functions if we take the closure, these are nothing but LP of R only. And since we're taking on a dense space and we have this convergent, this holds for all LP functions. And then this will imply then this holds for all, then this, uh, let me mention this star holds for all functions in LPR. Thus, we have T to be a, actually it's a T to C₀ semigroup, but in fact it turns out to be a group as well. So it's like a C₀ group as well. So we have other properties as well. Like one can check when we have also that, but it's more than a semigroup. So next part. So here we took the domain to be a real line, and real line has the property that we have translations. Like we can easily translate, but if we have a domain not so good, then like we have to consider translation in one direction only. So next part is when I'm considering the on LP spaces on LP uh, minus infinity to 0, take uh, for again I'm taking T to be this time a non-negative because of my domain is just in translate in the left hand side only. So in the right hand side only basically in T greater than equal to 0, define TT as uh, f of x minus t that holds for all x in minus infinity to 0 and f in LP minus infinity to 0. So we have this. So we have to again show that this turns out to be a C₀ semigroup. So one thing which we see that this time if I take, let's say, these times these operators are not how would I say, these are not isometric. Why? So like if I take t to equal to 1, so the I'm considering a domain of f, like it's just considering, even though it's I will consider it from x f x minus 1, and it will actually start my domain from minus 1 only. So it will be domain will be minus 1 to minus infinity, like basically minus infinity to minus 1 only. The portion of minus 1 in my 0, that is not there in the integration. So it's no longer being the same isometries. Let me type this. In this case, so these are not isometries. In this case, the operators TTT are not isometric, but of course T positive. But what do we have more? The integral area, the domain is decreasing, is becoming small. So but even if it's not isometry, these are contractions. In fact, one can prove that this T of T is actually one only. The norm is one only. Also is a one parameter semigroup. So again, semigroup properties again coming from the definition only, f of x minus t. So that thing is checkable. So that is not an issue. And with the now with the same ideas, we can prove that this uh, these translations like this thing. Now then there's one parameter semigroup. Finally, we have to choose third property that when I take the pointers limit, it has to be identity only, pointers identity. And again, we can, if you see, we nowhere use the fact that basically the special translation invariant property of real number. We just use the density of the step functions or the indicator functions, and the same one can use for this part as well. So using the same arguments in as in part A, we have basically this T is a C₀ semigroup. So as in one, we have T to be C₀ semigroup. So we don't have inverses, so it's again just a semigroup only. In the part C, now we are considering LP 0 to infinity. So this time again, what we are considering this for T to be greater than equal to 0. Uh, how to define a translation and define translations by define tt of fx is nothing but f of x minus t. So we have to take this to be less than equal to 0. Again, this holds for all x in 0 to infinity, and f in LP minus infinity or f in, sorry, 0 to infinity. So now how do we prove that this is a semi group? So we will start with we will prove this in a different manner. How do we do that? We do this as denote by s the C₀ semigroup of right translations on NPR defined in A but restricting the parameter to the 0 to infinity only. Now consider LP 0 to infinity as the, so we undefined the LP space. Follows as between LPR such that f restricted to minus infinity and 0 has to equal to 0. Of LPR So how we are like to proving this? We say that this clearly we have this thing that clearly ST. If I take so define denote this space by capital M, then ST of M actually is a subset of M only. So it's like it leaves the subspace invariant. So ST leaves M invariant. Once that is there, this implies that restriction T of S to the subspace, actually to the subspace, and it will coincide with this thing which we have defined just above. Subspace is a C₀ semigroup the operator Dt is isometric for all t non-negative. So next we have this final uh, LP space with the domain LP0. And again, how can we do this? You can do as goes like as in part 3 as well, as we follows as we argumented in the part 3. So how do we do that? We do it so analogously. Part B, we can define linear semigroup of right translations And let me define the translations. S on LP of minus infinity to 1. And then similarly to C, 1 shows that ST leaves C subspace LP01 of LP minus infinity to 1 invariant, and therefore we have this T. Therefore the restriction T of S2 LP01 is a C₀ semigroup. So this gives the proof that we can define we have a C₀ semigroup on LP01 as well. So with help of that we can define the C₀ semigroup on any arbitrary interval AB. Next, moving on, we will next we will see some applications of this theory of C₀ semigroups, and how we use these uh, densely defined operators and all that, and to actually construct this C₀ semigroup of contractions. So let me add one result which we'll be borrowing. And this result is actually known as the Lumer Phillips theorem. Let A be the we are again we have a densely defined operator. So if A is dissipative, that means I mean by dissipative, that means the real value of my u has to be less than or equal to 0 for all my u in A. Yeah? So like this is something like the minus part is minus A is monotone. It's like this only. Once if it's dissipative and the range of lambda naught I minus A is X for at least one lambda naught positive, then A generates a C₀ semi group ET of contractions. In fact, there's one more part which will not be requiring, but let me just mention it for the sake of completeness. So just for knowledge, so if A is the infinitesimal, infinitesimal generator of C₀ semigroup contractions. Then we have the range of lambda I minus A is whole x only for all lambda positive and is dissipative. And once we have this, let me also mention so once we have this, so our second question is we will solve this. So question number 2 is the solvability of the first order linear PD with Cauchy data del u by del t, and we have del u by del x for all t positive and x in R, and we have u0 is v only from x into R, and I'm taking so this is this. So we will so discuss the solubility. What we can do, we take x to be L2R and define A from dA subset of x to x by with um, A of phi equal to nothing but d phi by dx for phi in dA, where I'm defining the dA to be as I need the first derivative with respect to x, so it will define it to be as h1 of R. Then what do we have? We have then A phi, which phi, then a product in any product I'm taking. So this is nothing but the inner product of phi dash. So the inner product in L2 is just the integration with phi dash with phi only, and the integration by parts. So this is integrate by parts. I have this nothing to be minus of phi with phi dash and that is nothing but minus of phi dash with phi, and that is nothing but minus of a phi with phi. And what this basically implies, this implies the real part of a phi with phi is nothing but 0, and thus what we're with a is dissipative. That's the first property. Next, we would like to see that the range of this lambda I minus a is the whole of x. For given f in L2 of R, what do we basically have to do to prove this? There is a unique solution of lambda phi minus phi dash equal to f. So lambda positive. So we have this, and to solve this, this equality is if and only if we just take the integrate. This is just a first order PD OD, and I know that there's the integrating factor of this OD after multiplying with the integrating factor, which is nothing but e raised to power minus lambda x. So nothing but if I just multiply by e raised to minus lambda x, is minus of e minus lambda x phi whole dash into e minus lambda x fx, and then integrating from minus infinity to x. This is minus e minus lambda x phi dash, and then integration minus infinity to x e minus of it. Let me take this ps e lambda x fs ds. And this implies phi x equal to like after solving one can write this minus infinity to x e raised to lambda and x minus s fs ds. And what this basically implies, we actually found the if f is there, in fact I'm able to find the exact form of my phi only, as long as my lambda is positive. The range is the whole of x equal to L to R. So once that is there, using the result I've just mentioned, therefore A generates a C₀ semi group of contraction ET, and moreover UT is nothing but ET of V. And once that is there, this gives the solvability because we are able to find the function UT. Of our given equation. In fact, one can see that this ET actually will turns out to be, in fact, ET Vx is actually nothing but V of x minus t only. So this is the solvability. And once that, next we have another question, another PDE. Ut is equal to Laplacian of u, so t positive, and it's in Rd. So this is actually a heat equation we have. So we will see how to solve the result of this result. So the initial condition I'm considering is ux0 equal to Vx for x in Rd. So discuss the ability of this equation. So choose x equal to L to R, and I'm taking A to be just the Laplacian itself with its domain. I'm taking the domain to be dA is equal to H2 of Rd. Now, now for phi in dA, I have a phi with phi acted is nothing but the Laplacian of phi with phi, and that is minus norm of grad phi square, which is equal to 0. This implies operator A is dissipative. And the next we have to, this is the first property we want to show, and that is proof. Second, we would like to prove that range has to be equal to whole L to R RT. So another next claim is the range of lambda I minus A is nothing but L2 of RD. So it has to RD as well. Um, Consider the problem for F in L2 RD, lambda U minus Laplacian U equal to F, and X in RD and lambda positive. Note that gradient of U into gradient of characteristic plus lambda U with some function chi. So I'm just multiplying and integrating. So since lambda is positive, I can invoke the Lax-Milgram theorem by Lax-Milgram theorem. The above theorem has a unique solution U in H1RD for a given F in L2RD. So unique solution one can use the Lax-Milgram. We have this. So once we have the unique solution, then we can use this Fourier transformation and the Planck identity. We can actually prove the solution to be in H2 as well. With the regularity results by Fourier transformation. And here is the identity. We have U to be in H2 of RD for F in L2 of RD. Hence, the range of lambda minus A is nothing but L2 of RD. And this is implies A generates C₀ semigroup of contraction. So we have this problem to be solved, and in fact, one can note that this Fourier transform with the help of Fourier transformation. Note that with the help of Fourier transformation, one can write the semigroup as ATVX when upon 4 pi t dy 2. We'll see this in the coming videos that how can we write this. RD is for minus mod x minus 5 whole square or divided by 4t v by dy. Moreover, if V has compact support, then uxt, which is nothing but ET_Vx, is non-zero for all x in RD when I'm just taking t to be positive. And what this is by, this is the known as infinite speed of propagation of solutions. And also you also observe that when we have complex support again, then this uxt actually goes to 0 exponentially as mod x tends to infinity. Therefore, the effect at large distances, it's all the non-zero, is negligible. So even though it's exponential, but decay is exponential, so that is very negligible, like very less heat is there. But it reaches at just at infinite speed of propagation, just with the t little bit of any positive t, we have the solution to be non-zero. But for the very far ends, the value is very, very small. It's almost negligible. So that is the case. Next, we would like to prove some basic properties of this matrix exponential since we introduced the matrix exponential. Some basic questions based on the matrix exponential so that we have some good understanding of this matrix exponential. So the next question is question number 4. So the question number 4 is let several questions will be based on our matrix exponential only. So suppose AT is minus A. So A is a skew symmetric matrix. Prove that EA is an orthogonal matrix. So what do you mean by orthogonal? Orthogonal means A trans basically if we take B is equal to EA, then EA, then B transpose P is equal to identity, which is equal to B times P transpose. Solution. So one thing which to prove this, it is actually follows directly. If we have, we know that A times A transpose is nothing A times minus A, and which is nothing that can be written as minus A times A, which is A transpose A. So basically A and A transpose commutes. And once that is the case, we know that E of this thing, and moreover, we have to consider the B transpose. So B transpose is nothing but E exponential of A transpose. So this is nothing but actually identity plus A transpose, and then we have A. Actually, it will be A square whole transpose, but that is A transpose whole square. We have a 2 factorial, and then we have A transpose 4 is power 3 upon 3 factorial, and so on and so forth. But what is A transpose? A transpose is minus A only. So 1 minus A, and then we have A square by 2 factorial minus A cube by 3 factorial, so on and so forth. But if we see, this is nothing but the exponential of minus A only. But again, that is actually, so basically E of A whole transpose is nothing but E of A raised power transpose. Yeah, so EA whole transpose is nothing but E of A transpose, and that is actually E of minus A. And since they commute, then we have E of, so B times B transpose is nothing but EA, E of A whole transpose, E of A into E of minus A, but they commute. As they commute, I can write this whole as E of A plus minus A, which is A of 0 matrix, and we know that E of 0 matrix is nothing but identity only. The other way we can prove in the similar lines, and for this we have this will imply E is actually an orthogonal matrix. Another question we have is, if I take if A square is equal to A, then find E raised power of A, or basically I would say find, I would say um, reduce E in simpler terms. Simpler means the polynomial in A only. So if I A, E raised power of A, it will be identity plus A square by 2 factorial plus A cube by 3 factorial, and so on and so forth. And this is nothing but again identity plus A. Then since A square is A, this means my A raised power of N is also A. This is A by 2 factorial, A cube by 3 factorial, but again A cube I can reduce into A only. And this whole can written as identity plus A I can take to be common. 1 upon 1 plus 2 factorial, 1 upon 3 factorial, so on and so forth. And this whole can be written identity plus A times. So this is nothing but the expansion of E minus 1, and this is the simpler form. One more example. So this commutatively to one more example. Let A equals to 1, 0, 0 and B equal to 0, 1, 0, 0. Then show that E raised power A plus B is not equals to EA times EB. So first of all, we have to evaluate this E of A, E of B, and E of A plus B. And then we have to show that finally that we don't have this commutativity. Or since the commutativity is not there, we don't have this equality when the commutativity is there. So when my A is this, my A square will be again this same matrix, and this is nothing but A only. So then from the last question, I know that e to the power of A is can be given as this only. Identity plus A times E minus 1, which is nothing but 1001 plus 1000 times E minus 1, which is nothing but 1 plus E minus 1, 0, 0, 1. And that is E001. And next we have E of B. So first of all, let us consider what is B is 0, 1, 0, 0. So if I can evaluate B square, that is 0, 1, 0, 0, 0, 1, 0, 0. And if you see that actually nothing but 0, 0, 0 matrix, so 0 only. So B n is 0 when n is greater than or equal to 2. This is of B will be nothing but one identity plus B only. And that is 1, 0, 0, 1 plus 0, 1, 0, 0, which is 1, 1, 0, 1. Now A plus B, let's name this to C only, and this is nothing but 1, 1, 0, 0. So we now want to find a general formula of E is C Cn. So C square is 1, 1, 0, 0, 1, 1, 0, 0, which is 1, and we have again 1, 0, 0. So again, this is C only. So this gives actually e to the power of C is nothing but again with the previous formula. This is identity plus A times 1 minus identity, which is 1, 0, 0, 1 plus 1, 1. So it's sorry, it's not 1. This is C. 0, 0, 1 minus C. And it actually gives E. So it's not 1, sorry, 1 minus not 1 minus E, it's E minus 1. So this is E minus 1, 0, 1. Now we have all the things. So I know this is this. Now E of A times E of B. If I see this is E001, and EB is 1110. If we have error, this is E, and this is another E. This is 0 and this is 1. So in view of this, if I take this to be star, it needs to be double star. So in view of star and double star, we have E of A times E of B is not equal to E of A plus B. And the final question which I like to discuss is this thing, this question. So if we let trace of a matrix to be like we traces some of the diagonal entries. We'll show that if A is diagonalizable, then determinant of this e raised power of A is actually nothing but e raised power of trace of A. In fact, this is true for any square matrix, but let's prove this for the diagonalizable matrix. So since A is diagonalizable, A can be written as P inverse, where D is a diagonal matrix and P is actually an invertible matrix. Then first claim e raised power of A will be P times e raised power of D, P inverse. So e raised power of A is nothing but identity plus A square by 2 factorial, A cube by 3 factorial, so on and so forth. And this is identity P inverse, and A square if we evaluate, this is nothing but actually P D square P inverse by 2 factorial, and then we P D cube P inverse 3 factorial, so on and so forth. And this whole can be physics can be done P times identity plus D plus D square by 2 factorial times D cube by 3 factorial, so on and so forth, times P inverse. This whole can be done P times ED P inverse. So this is our claim. This was our claim. Now finally, we have to evaluate the e raised power of D. E raised power of D is nothing but if you see its identity plus D square by 2 factorial D cube by 3 factorial, so on and so forth. But this, if you see, can be written as identity. This is a diagonal matrix, so I denote D1 and D11, D222, and DNN, all 0 into 0. And this will divide by 2 factorial, 1 by 3 factorial. So it's 1 only, 1 by 1. This is 2 factorial. And if take the matrix, this will have D square, when D is diagonal, this will be D11 square, D22 square, and DNN square, all 0, 0, so on and so forth. This C, this is nothing but the matrix 1 plus D11 by 1 factorial, D11 whole square by 2 factorial, and 1 plus DNN by 1 factorial plus DNN square by 2 factorial dot dot 0 and 0. And this is nothing but E of D11 up to E of DNN 0, 0. That is there. This is my e raised power d. Thus, what we end up with this determinant of e raised power of a is nothing but determinant of p e raised power of t p inverse, and that is nothing but determinant of p times determinant of e raised power of t times determinant of p inverse, and this is nothing but actually determinant of ed only, and this because determinant p inverse is determinant of p whole inverse, and this is nothing but actually e raised power of t11 plus t22 dn. But what are DDI? These are the eigenvalues of my matrix A, and this is eigenvalues, and the sum of eigenvalues is nothing but trace of A only. And that is it. We have our result. With this, we stop our session today. Thank you.